Hello everyone. So in this video, I am giving you an example, a molecule, so we can assign hybridization to every atom in this molecule and also discuss a little bit about the location of lone pairs in terms of orbitals and the orbitals used for bonding for each of these atoms, okay? So if we look into the molecule, this is a line and angle notation given. As you should know at this point, there is one hydrogen here which do not need to be shown, two hydrogens here, everything else is shown, and I'm giving also here the Lewis structures, two lone pairs for each oxygen atom and one lone pair for the nitrogen. Okay, so I'm gonna start by this carbon here and this carbon over here. So as you can see, these two carbons, they do not have any pi bonds, so all they have is sigma bonds, each of them having 4 sigma bonds. Okay, if you cannot see the 4 sigma bonds, please stop the video, look at the molecule and practice, right? So this carbon is bonded to 2 hydrogens and then to 1 carbon and another carbon here. This carbon is bonded to 1 hydrogen, an oxygen, a carbon and a carbon. So because these 2 carbon atoms do not have any sigma bonds, any pi bonds, I'm sorry, they have 4 sigma bonds, so we assign the hybridization of sp3 to each one of them. Remember once again that whenever we assign sp3 hybridization, it means that we are talking about 4 sp3 hybrid orbitals, so that's important to keep in mind and something I want to emphasize. So 4 sp3 hybrid orbitals. In this case, the 4 sp3 hybrid orbitals are used for 4 sigma bonds, okay? In this case, once again, a sigma bond to the carbon, a sigma bond to this carbon here, a sigma bond to the oxygen, and a sigma bond to the hydrogen not shown, okay? So what about the geometry? Both sp3 hybridized carbons are tetrahedral structures, so the geometry is like this, meaning that the bond angle in between each sigma bond is 109.5 degrees, okay? So next question is there any other um, sp3 hybridized carbon in this or atom in these pictures? And indeed there is one. So if we look at this oxygen here, so that oxygen has no pi bonds whatsoever. Okay, this oxygen over here has no pi bonds, so therefore this is also an sp3 hybridized oxygen. Uh, because it's sp3, since it has no pi bond, there are 4 sp3 hybrid orbitals around this oxygen atom. So first we look at how many sigma bonds in this oxygen. 2 sigma bonds, so 1 to the hydrogen and 1 to this carbon. So 1 sp3 is used for 1 sigma bond, I'm gonna say, to the hydrogen. Another sp3 is used to for another sigma bond. Sorry about this. In this case, to the carbon atom. And then the 2 remaining sp3 hybrid orbitals are used for what? For the lone pairs. Lone pair 1 and lone pair 2. Okay, so guys, this is very important because this is how you will learn resonance theory later on. So we need to really understand that in this case, for an sp3 hybridized oxygen, the 2 lone pairs are in an sp3 hybrid orbital. Therefore, the angle between these 2 lone pairs is expected to be a little lower than 109.5, around 105 degrees. Okay? Okay, so let's move on to the next set of atoms. So I'm gonna just point toward this carbon. This carbon has 1 pi bond. I'm gonna color code it with blue. So this carbon has 1 pi bond. Because it has 1 pi bond, this carbon must be sp2 hybridized. Okay, the oxygen of the carbonyl compound is also having, I can see this oxygen having 1 pi bond, so that oxygen is indeed sp2 as well. So I'm gonna say sp2. And remember, the nitrogen from the amino functional group here, this is an amide functional group. So remember how we discussed in another video that atoms with lone pairs, so the nitrogen has a lone pair next to an sp2 hybridized atom, they will also be sp2 hybridized, okay? So these three atoms are sp2 hybridized. Remember when we talk about sp2, quickly we have to think about how many sp2 hybrid orbitals, 3 sp2 hybrid orbitals, and the fourth is a pure orbital for a pi bond. So each one of these sp2 atoms will have an sp2 hybrid orbitals around them, and the fourth orbital will be a pure orbital, once again used for the pi bond. So I'm gonna use this diagram to then locate the orbitals used for bonding of each of these atoms. So for the carbonylic oxygen, so this one over here, so the carbonylic oxygen has a pi bond, right? So once again, color coding this. So the carbonated oxygen here has a pi bond to this carbon. So this pi bond is through a pure orbital. So the p orbital of the carbonylated oxygen is used for a pi bond. That we should know. What about the 3sp2? So this oxygen has how many sigma bonds? One sigma bond. So one sp2 orbital is used for the sigma bond, in this case to the carbon, and there are two vacant sp2 hybrid orbitals, which obviously will be having the two lone pairs. So the two sp2 orbitals will be used for the lone pairs. So that's very important, guys. So let's keep this in mind. For this carbonylic oxygen, once again, the two lone pairs will be located in two sp2 hybrid orbitals. The third sp2 will be for the sigma bond, and then the p orbital for the pi bond. So remember, once again, the geometry, guys, of an sp2 hybridized carbon is here. So I'm showing the geometry here, right? So the three sp2 hybrid orbitals are forming an angle of 120 degrees between them, and then perpendicular to these three hybrid orbitals, you have the p orbital, which is used for the pi bond. Angle, once again, between the pi bond and the sigma, and the sp2 hybrid orbitals is 90 degrees. So for this oxygen, the angle between the lone pairs and the sigma bond obviously has to be 90 degrees, okay? The lone pairs, the angle between the lone pairs and the pi bond, it has to be 90 degrees. So the lone pairs, once again, are located in two sp2 hybrid orbitals, and the pi bond is through the pure orbital. So the angle between these two is 90 degrees, okay? So what about this nitrogen here? So this nitrogen is also sp2 hybridized. Also want to do here an orbital analysis for this nitrogen atom, because we're going to be using this in the next few classes for resonance. So once again, this nitrogen is sp2 because it has lone pairs, and it's next to an sp2 atoms, right? Atoms with lone pairs next to an sp2 atom will also be sp2 hybridized. The moment we say it is sp2 hybridized, we have three sp2 hybrid orbitals and one p orbital, right? So how many sigma bonds do we have in this nitrogen? Three sigma bonds, one to the carbon and two to the hydrogen. So the three sp2 hybrid orbitals will be used for sigma bonds. One sigma bond to the carbon, and then one sigma to the hydrogen, and another sigma to the other hydrogen. Therefore, guys, the pure p orbital, which in this case is the fourth orbital, will be having the lone pair. Okay, very important. So this lone pair here, in this case, remember how I said that when we did the orbital analysis for the oxygen, the lone pairs are in sp2 hybrid orbitals, and how the angle between this and the pi bond is 90. So for this nitrogen atom, which is also sp2, when we do the orbital analysis, we can see how, because it has 3 sigma bonds, the 4th p orbital is used for what? For the lone pair. So in this case, once again, the lone pair is in the pure p orbital, and the 3 sigma bonds are in hybrid sp2 orbitals. So the angle, once again, between the lone pair here and the sigma bonds of this nitrogen continues to be 90 degrees. Okay, and more importantly, this pure p orbital is parallel and in the same plane to this p orbital and to this p orbital. So these 3 p orbitals, guys, from the oxygen sp2, from the carbon sp2, and from the nitrogen sp2 are parallel to one another, and they are perfectly aligned. And this is very important for resonance. I'm gonna draw this here quickly so you can see. So the p orbital of the oxygen is here, forming, gonna turn it like this slightly so you can see it better, forming a pi bond with the p orbital of the carbon, and there is also a p orbital next to them, parallel, perfectly aligned with them, in this case having the lone pair of the nitrogen. That's very important to really understand. And then finally, we have this carbon atom here, and the second carbon atom next to it. These 2 carbon atoms, they do have 2 pi bonds. Because they have 2 pi bonds, they need to use 2 p orbitals for these 2 pi bonds, so they will be sp hybridized. So any atom with 2 pi bonds will be sp hybridized. The geometry of an sp hybridized carbon is like this. I'm showing it over here. Okay, so look at how the geometry looks like. So you have the 2 sigma sp hybrid orbitals are here. So let me do the orbital diagram for an sp so we can track this. So when we have sp, obviously sp, so 2 hybrid orbitals, 1s and 1p, were used for combination, and then we have 2 pure p orbitals for pi bonds. Okay, so 1 p orbital for a pi bond, second p orbital for a pi bond, that's for the triple bond, right here. And then let's say for this carbon here on the left side, 1 sp is going to be used for a sigma with a hydrogen to the left, and 1 sp for the sigma to the carbon on the right. The 2 hybrid orbitals of this carbon, one is used for the sigma to this carbon, and the second one is used for the sigma to this other carbon. Okay, let's keep that in mind. So once again, the geometry is linear, right? So the 2 sp sigma here, the angle between them is 180. They are linear. And then we have the 2 p orbitals around each carbon forming 90 degrees between them, right? So each p orbital is 90 degrees from the next. Therefore, the triple bond looks like this, okay? So it's like a cylinder of electrons with 2 pi bonds around the carbon forming the triple bond, and the sigma bonds 180 degrees from each other. So that's how you guys analyze this. Once again, focus on the number of pi bonds to assign hybridization. Once you do that, keep in mind that for sp3 there are 4 sp3 hybrid orbitals, so you can assign which orbital is used for what. For sp2, always you have 3 sp2 and 1 p, same thing, so you can locate which orbital is used for what. And for sp, you have 2 sp and 2 p, so you can assign the orbitals. This is extremely important because then you will see later on what are the p orbitals that are parallel and involved in the localization of molecules. Thank you.